When writing programs, many things can go wrong. Our programs may encounter an error and terminate. Usually, these errors happen because of programmers' mistakes or bad data that we get from the user or resources not being available. For example, we might need to open a file, but if that file doesn't exist, our program is going to crash. It's your job as a programmer to prevent your application from crashing in these kind of situations. Instead, we want to display a proper error message to the user, like, hey, this file doesn't exist. So let's take a look at a few examples. I'm going to define a list of numbers with 2 items and then print the third item. When we run this program, we get this error, index error. This happened in this file, app.py, on line 2, and here's the statement that generated this error. In programming, we refer to this kind of error as an exception. An exception is a kind of error that terminates the execution of a program. More specifically, we say this line, this statement, threw an exception. And this is an example of an exception that was thrown because of the programmer's mistake. Here's another example. Earlier you learned about the input function to get input from the user. Let's say we ask for the user's age. You know that this function returns a string, so we need to convert it to an integer and then store it here. Now, instead of running this using the code runner, let's go to the terminal and run Python or Python 3 app.py. The reason I didn't run this using code runner is that by default, code runner runs our programs in the output window, which is read-only, so we cannot enter data. So here in the terminal, let's run this program. If we enter a non-numeric value like a, our program crashes. In this example, we got an exception of type value error. So, as I told you before, it's your job as a programmer to handle these exceptions and prevent your application from crashing. And that's what I'm going to show you next. In this lecture, I'm going to show you how to handle exceptions in your programs. So continuing with the code from the last lecture, to handle the value error exception here, we need to put the statement in a try block. So we add try, colon, we indent it, and then after try, we need to add an except clause. What is the type of the exception that we get if the user enters a non-numeric value? That's a value error exception. You saw that in the last lecture, right? So we add the except clause, and then we'll print a friendly error message, like you didn't enter a valid age. So this is how this works. When Python sees a try block, it will execute every statement in this block. If any of these statements throws an exception, the code in the except clause will be executed. If we don't have any exceptions, this code will not be executed. Let me show you. So save the changes. Back in the terminal, let's run the program. I'm going to enter a valid age. So our program completed successfully. No error messages. Beautiful. I'm going to run the program one more time. This time I'm going to enter A for the age. So we got a friendly error message and our application didn't crash. This is the important thing about handling exceptions. If you don't handle exceptions properly, your program will crash. So in other words, if we add another statement here, let's print execution continues. In this example, because we are handling this exception properly, this statement will be executed. Let me show you. So back in the terminal, let's run the program one more time. Enter A. We got our friendly error message. And also, you can see the execution of our program continued. In contrast, in the last lecture where we didn't have the try block, if we put this print statement after getting user's age, this line would not be executed. Okay? We also have an optional else clause here. So else colon. And what we put inside this block will be executed if no exception is thrown in the code that we add in the try block. So let's print a message like no exceptions were thrown. Save the changes. Back in the terminal, let's run this one more time. I enter a valid age. You can see this message, no exceptions were thrown. So what we have in the else clause will only be executed if we don't have any exceptions. This is very similar to our for else loops. Remember for else? Earlier, when I talked about for else loops, I told you that the else clause is executed if we don't break out of the for loop. In other words, if the for loop completes, then the else clause is executed. So here's a basic structure for handling exceptions. Now, one more thing before we finish this lecture. Here, when handling the exception, we can optionally define a variable that will include the details about the exception, mostly the error message and sometimes additional arguments. So here we add as and then define a variable like error or X for exception. So after this error message, let's just print X. I'm also going to print type of X. Now let's run the program one more time. Enter A. So here's our friendly error message. Below that, we have the actual error message that is included in the exception, invalid literal for int with base 10. Now, this is very technical to show to an end user, so we're not going to print it on the terminal. This is just for demonstration. And below that, you can see the type of this exception. It's an object of type value error. All right, I've simplified the code from the last lecture. Now let's extend this example. Let's make up a magic formula like x factor equals 10 divided by h. Save the changes. Back in the terminal, let's run this program one more time. I'm going to enter 0 as the h. What happened? Our program crashed again. We got a different kind of exception that is a zero division error. Because in programming, we cannot divide a number by 0. So the statement on line 3 threw an exception, but we don't have a matching except clause for that kind of exception. In other words, in this code, we're only handling value error exceptions. And that is why our program crashed. So to solve this problem, we can come back here and add a second except clause, except, and specify a different kind of exception. In this case, zero division error. Now below that, we can print a message like age cannot be 0. Back in the terminal, let's run the program one more time and enter 0. Okay, beautiful. Our program didn't crash. Now let's take this to the next level. Let's imagine if the user enters 0 for the age, we want to print the exact same error message. So I'm going to copy this and paste it here. Now our code looks a little bit repetitive. We have repeated this message, and that means if in the future we want to change this message, we have to change it in 2 places. There is a better way to handle this situation. In front of this except clause, we can specify multiple types of exception. So if the exception that is thrown matches any of those exceptions, then the code that we have in the except block will be executed. So here, we need to add parentheses to specify multiple types of exceptions separated by comma. So comma, 0 division error, and close parentheses. Save the changes. Now with this change, technically we don't need these 2 lines. We can delete them. But temporarily, I'm going to keep them to show you something interesting. So back in the terminal, let's run this one more time and enter 0. Note that we get a single error on the terminal. In other words, the code that we have in this except block was not executed. Otherwise, we would see this message twice. So here's the lesson. When Python executes the code that we have in the try block, if any of the statements throws an exception that matches one of the except clauses, that except clause is executed and the other except clauses are ignored. So to clean up this code, we can delete these 2 lines. That is better. There are times that we need to work with external resources like files, network connections, databases, and so on. Whenever we use these resources, after we're done, we need to release them. For example, when we open a file, we should always close it after we're done. Otherwise, another process or another program may not be able to open that file. So let's take this example to the next level. Here in our try block, First, I'm going to open a file. So we call the open function. And let's open app.py here. This returns a file object. So let's get that here. Now, when we're done, we should close this file object. So this file object has a method called close. Now, the problem with this code is that this statement will not be executed in case of an exception. In other words, if one of these two lines, line 3 or line 4, throws an exception, the control will be moved to our except clause, so what we have on line 5 will not be executed. One solution is to move this down here, but again, the problem is that this will only be executed if we have an exception. If we don't have an exception, the control will be moved here, so our file will not be closed. So another solution is to duplicate this here, and duplication is a bad practice in programming. You should not repeat yourself in your code. So what is the solution? The solution is to use the finally clause. Let me show you. So I'm going to delete this line here and add a finally clause at the end. This finally clause is always executed whether we have an exception or not. And we use it to release external resources. So this is the perfect place to close files, database connections, network connections, and so on. In the last lecture, you learned that we use the finally clause to release external resources. Now we have a shorter and cleaner way to achieve the same thing, but without the finally clause. But it doesn't always work. It works with certain kinds of objects. Let me explain. So on line 2, I'm going to make a couple of slight changes. Instead of getting the return value of the open function, we prefix this with the with statement. And then we'll get access to the return value of this function by typing as file. So this is the file object that the open function returns. After that, we add a colon. So obviously here we're going to have a block. In this block of code, we can work with this file object. For example, we can read something from this file or write to it and so on. So for now, let's just print file opened. Now, whenever we open a file using the with statement, Python will automatically call file.close whether we have a finally clause or not. In other words, the with statement is used to automatically release external resources. So now we can delete these two lines from here. That's better. But let's dive deeper and see how this exactly works under the hood. So look at this file object, file dot. These are the members of the file object. We have methods that start with two underlines, and we refer to them as magic methods. In the next section where I talk about classes and objects, you're going to learn about these in detail. But here we have two magic methods that you should be aware of. We have enter and exit. When an object has these two methods, we say that object supports context management protocol. Again, in the next section, I'm going to talk about this in more detail. So if an object supports the context management protocol, or in other words, if an object has these two methods, enter and exit, we can use that object with the with statement. Python will automatically call the exit method, and there it will release external resources. That is the reason we don't need a finally clause here. Now, to take this to the next level, there are times that you might be working with multiple external resources. Let's say we want to read some data from one file and write it to another file. So how do we do that? Well, here before the colon, we can add a comma and open another external resource, like another file. So open, let's say, another file.txt as we give it a variable name, like target. With this, Python will automatically release both these external resources. Now I'm going to delete the second one here because we don't have a file called another.txt. So when we run this program, we'll get an exception and our program will crash. So delete. So this is all about the with statement. So far, you have learned how to handle exceptions, but you can also raise or throw exceptions in your own code. Let me show you an example. So I'm going to define a function. Let's call it calculate x factor. This function takes age and simply returns 10 divided by age. Now, in this example, age cannot be 0 or less. So we can have an if statement here. If age is less than or equal to 0, we can raise an exception. So we use the raise statement and then specify the type of our exception. So far, you have seen a few types like value error, zero division error, and so on. In Python, we have various kinds of built-in exceptions. If you go to Google and search for Python 3 built-in exceptions on this page, we can see all the built-in exceptions in Python and what they're used for. Down the bottom of this page, you can see the complete list of these exceptions. So as you can see here, we have a hierarchy, like a parent-child kind of relationship. At the very top, we have base exception. Below that, we have a few children. One of them is exception. Below exception, we have arithmetic error. And below that, we have zero division error. So these are the built-in exceptions in Python, and they're sufficient for most cases. But you can also define your own exception types. It's not something that you do that often, but it is something that you can do for sure. In order to do that, you have to learn about classes, and that's the topic for the next section. Back to our code. In this case, we want to raise a value error exception. In parentheses, we can specify an error message, like age cannot be 0 or less. So we have this function that raises or throws an exception if we give it an invalid argument. Somewhere else in our program, we're going to use this function. So we call calculate x factor and pass, let's say, -1. Now, when we run this program, we can see our program crashed with a value error exception. And here's the message: age cannot be 0 or less. Obviously, this happened because we didn't handle exceptions here properly, so we didn't have a try block. To fix this issue, let's add a try block with an except clause of type value error. Let's give this exception object a name like error. And here we can simply print this error. Now let's run the program one more time. So here's our error message, and our program didn't crash. Beautiful. So this is how you can raise exceptions in your code. But this is not something that I advise you to do. I only explained it here because you will see this in other people's code. As I will show you in the next lecture, raising exceptions is costly. So in this example, instead of raising an exception here and then handling it below this function, we could take a different approach that would result in better performance. That's what I'm going to show you in the next lecture. As I explained in the last lecture, when writing your own functions, prefer not to raise exceptions because these exceptions come with a cost. And that's what I'm going to show you in this lecture. So from the timeit module, I'm going to import a function called timeit. With this function, we can calculate the execution time of some Python code. So this is how it works. Imagine we want to calculate the execution time of this piece of code. We define a variable, let's call it code1, and set it to a string. This string should include our Python code. So I'm going to use triple quotes because our Python code is spread across multiple lines, and we terminate it here. So this is one piece of code. Now, after that, we call timeit. As the first argument, we pass our Python code. That is our code1 variable. Now here we have a keyword argument, number. We set this to the number of times we want to execute this piece of code. So let's set it to 10,000 so we can see the difference. Now this function returns the execution time of this piece of code after 10,000 repetitions. Now this function will execute our Python code 10,000 times. It will calculate the execution time and return it. So we can simply print it on the terminal. I would like to add a label as well. Let's say first code. Now, open up the terminal window. You can run this using Code Runner. So type Python app.py. You can see our program was executed 10,000 times, and we got 10,000 messages here, and here's the execution time. Now to clean this up, let's go back to our except clause. I don't want to print this error message. So let's use the pass statement. This pass statement is a statement that doesn't do anything. And we need to use that here because we cannot have an empty except block. Okay? So save the changes, back in the terminal. Let's run this one more time. So here's the total execution time. Now let's try a different approach. Back in our calculate x factor function, instead of raising an exception if age is 0 or less, we can return a value like none. So I'm going to select this entire code, copy it, then paste it. Let's change this variable's name to code2. In this implementation, instead of raising an exception, we want to return none. So none is an object that represents the absence of a value. In this new implementation, we don't need a try block, so we can simplify our code. Let's delete that, as well as the except clause and the pass statement. We simply get the x factor. We can store it in a variable. So instead of handling an exception, we can compare this x factor with none. So if x factor equals none, then let's just pass. So immediately you can see this code is simpler than the previous implementation. And as you will see in a second, this will be executed almost 4 times faster. Let me show you. So down the bottom, I'm going to duplicate this line, change the label to second code, and replace code 1 with code 2. Save the changes, back in the terminal. Let's run the program. So here's the execution time of the first implementation. As you can see, our second implementation was almost 4 times faster. Now there is a caveat here. We see this difference when we execute this piece of code 10,000 times. So if you run the code once, you're not going to see any differences. In other words, if you're building a simple application for a few users, raising exceptions in your functions is not going to have a bad impact on the performance of your application. But if you're building an application where performance and scalability is important, then it's better to raise exceptions when you really have to. As a general rule of thumb, when you want to raise exceptions in your functions, think twice. See if you can handle the situation with a simple if statement. Whether there is a performance difference or not, your code will end up being a little bit cleaner. So, raise exceptions if you really have to. In this section, we're going to look at classes, which are extremely important in Python programming or in programming in general. So let's start with an example. I'm going to define a list of numbers like this. Now, you have learned that when we use the dot notation, we get access to all these functions, or more accurately, methods in list objects. So every list object in Python has these methods. Now, wouldn't that be nice if we could create an object like shopping cart, and this object would have methods like add, remove, get total, like this. Or as another example, wouldn't that be nice if we could have a point object with methods like draw, move, or get distance to get the distance between this point and another point. That's when classes come to the rescue. So a class is a blueprint for creating new objects. Throughout the course, you have heard the term class. For example, let's define a variable and set it to an integer, and then print its type. When we run this program, what do we see here? A class of int. So in Python, we have a class called int for creating integers. Similarly, we have classes for creating booleans, lists, dictionaries, and so on. So every object that we have in Python is created using a class, which is a blueprint for creating objects of that type. In this section, you're going to learn how to create custom classes like customer, shopping cart, point, and so on. Now, before we get started, let's define a few terms. Once again, a class is a blueprint for creating new objects. An object is an instance of a class. As an example, we could have a class called human, and this class would define all the attributes of humans. Then we could create objects like John, Mary, Jack, and so on. So this is the difference between classes and objects. Now, a lot of people use these terms interchangeably, but technically, a class and an object are different. So, now you know what classes are and how they're useful. In the next lecture, I'm going to show you how to create a custom class in Python. All right, now let's see how we can create a point class in Python. So we start with the class keyword. Then we give our class a name like point. Note that here I'm using Pascal naming convention, which is different from the naming convention that we use for naming our variables and functions. To name our variables and functions, we use all lowercase letters and we separate multiple words using an underscore. But to name our classes, we use a different convention, which is called Pascal naming convention. And basically, it says that the first letter of every word should be uppercase, and we shouldn't use an underscore to separate multiple words. Here's an example. We can call this class myPoint. You can see that the first letter of every word is uppercase, and there's no underscore here. Okay? So let's change this back to point. After this, we add a colon to indicate a block. In this block, we'll define all the functions related to points. For example, we can define functions for drawing a point, for moving this point to a new location, or getting the distance from this point and another point. Here's an example. We define a function called draw, parentheses. Now, all functions in our classes should have at least one parameter, and by convention, we call that parameter self. You will see what this is in a minute, so bear with me. Now we add our colon, and let's just print the word draw on the terminal. So now we have a class or a blueprint for creating point objects. Every point object that we create will have this draw method. Let's take a look. So to create a point object, we call this class like a function. There you go. Now this returns a point object that we can assign to a variable like point. So if we use the dot operator, you can see we have the draw method as well as a bunch of other methods that we didn't define. But our point object got these methods from another object in Python through a mechanism called inheritance. We'll look at that later in this section. Now, if we print type of point, now let's run this and see what we get. We get a class of main.point. This main you see here is the name of our module, and we're going to look at that later in this section. So this is the type function that you have seen before. We have another useful function called isInstance. Sometimes we have an object, and we want to know if this object is an instance of a given class. So let's see if this point object is an instance of the point class. Now let's print the result on the terminal and run our program. So obviously, this point object is an instance of our point class. However, if we change this to int, obviously our point object is not an instance of the int class. So when we run this program, we get false. So this is how we create custom classes in Python. So far, so good. But our point objects need some initial values like x and y. To set these values, we need a constructor, and that's the topic for the next lecture. So here when we create a point object, we want to supply initial values for x and y coordinates, like this, 1 and 2. To achieve this, we need a constructor, which is a special method that is called when we create a new point object. Let me show you how to create a constructor. So, in our point class, we define a new function. The name of this function should be double underline, init, double underline. This is a special method that we call a magic method. In Python classes, we have several magic methods, and you're going to learn more about them throughout this section. So this magic method is called a constructor, and it's executed when we create a new point object. Now, earlier I told you that all the methods that we define in a class should have at least one parameter, which we call self by convention. You will see what this is shortly. So we add self, and then optionally we add any additional parameters for initializing a point object, like x and y. Now, what is this self? Self is a reference to the current point object. For example, here on line 9, when we call the point class, Python will internally create a point object in memory and set self to reference that point object. Now, this point object has a bunch of methods that you have seen before. For example, when we use the dot operator, you can see all the methods in this point object. But an object can also have attributes, which are basically variables that include data about that object. For example, we can have attributes like x and y that we can easily print on the terminal. In other words, a class or an object bundles data and functions related to that data into one unit. Once again, as a metaphor, think of a human. A human can have attributes like eye color, height, weight, and so on, as well as functions like walk, talk, and so on. Okay? So, back to our constructor. You learned that self is a reference to the current object. So we can use that to set the x and y attributes, like this, self.x. We can set it to some default value like 0, or this x argument that we receive in this method. Similarly, let's set self.y to y. Now with this code, when we use the dot operator, look, we have the draw method as well as the two new attributes x and y. So we can simply print point.x on terminal. Let's take a look. Run this code. As you can see, x is 1. Now, back to our draw method. Here again, we have this self parameter. So using this, we have a reference to the current point object. And with that, we can read the x and y values and print them on the terminal. So here, I'm going to change this implementation and pass a formatted string like this. Point, parenthesis. Here, I want to pass self.x, then comma, and then self.y. So using self, we can read attributes of the current object, or we can also call other methods in this object. Now let's change line 11 and simply call point.draw. Save the changes, run the program, and this is what we get. Now what is interesting here is that when calling the draw method, we didn't have to supply a value for the self parameter because Python does that by default. Now technically, we could come back here and pass this point object as a reference to the current object, but this is really unnecessary and it makes our code busy or noisy. So here's what you need to take away. The methods that we define in a class should have at least one parameter, which by convention is called self. And this references the current point object that we're working with. When calling methods of an object, we never have to supply a value for this parameter. Python interpreter does that for us. So in the last lecture, we defined two attributes for our point objects in the constructor of the point class. So now, whenever we create a new point object, this point object will have these attributes by default. We can also define an attribute after we create a point object. So here we can set point.z to 10 because objects in Python are dynamic, similar to JavaScript. So we don't have to define all the attributes in a constructor. We can define them later whenever we need them. Now here's what is important for you to understand. All these attributes we have defined so far, x, y, and z, these are instance attributes. In other words, these are attributes that belong to point instances or point objects. So every point object can have different values for these attributes. Here's an example. We have one point object with these values. We can create another point object with different set of values, and then draw that on a terminal. When we run this, you can see we have 2 point objects, and these are completely independent of each other. Each point has its own attributes, just like John and Mary can have different eye colors. So these are instance attributes. But we can also define class attributes, and these are attributes that we define at the class level, and they are the same across all instances of a class. As a metaphor, we can say all humans have 2 eyes and 2 ears. So these are the attributes that we define at the class level, and they are shared by all instances. So back to our point example, here we can define a class level attribute in the body of this class like this: default color. Now for simplicity, I'm using a string here because we don't want to worry about using color objects. That's a different story. So now we have a class level attribute, and we can read this via a class reference or an object reference. Let me show you what I mean. So here on line 12, we have a point object. We can use this object reference to get access to the default color attribute and then print it. But we can also use the point class to get access to this attribute. Let's print both of them and run our program. So we get red and red. Now, as I told you before, class attributes are shared across all instances of a class. So here, before we print the default color, if I change point.default color to, let's say, yellow, note that here on line 11, I'm using a class reference, so I'm not working with any point objects. I'm working with the point class. Now, when we run this program, you can see that the default color of this point object is changed to yellow. Similarly, here we have another point object. If we print another .default color, the value of this attribute is also changed. So, class level attributes are shared across all instances of a class. If we change their value, the change is visible to all objects of that type. Now, in practical terms, you will be using instance attributes most of the time, but there are times that you may want to define a class level attribute that is shared across all objects of a given type. In the last lecture, you learned about instance versus class attributes. We have the same concept around the methods that we define in a class. So we have instance method as well as class methods. In this example, both these methods that we have defined in the point class are instance methods. So we can call them using an instance of the point class, using an object. Generally speaking, you use these instance methods whenever we need an object reference. For example, when drawing a point, we really need to work with a specific point object. That is why this draw method is defined as an instance method. But there are times that we don't really need an existing object, and that's when we use a class method. For example, let's say in our program, there are a lot of cases where we want to create a point with these initial values, 0 and 0. This is one way to create a point object, and that's perfectly fine. But we can come up with a different way to create a point object with these values, like this. Point, so note that I'm using a class reference, then dot 0. In this case, 0 is a method that is defined at the class level, and when we call it, it will return a point object initialized with these values. So we can get this point object and assign it to this point variable. Now, in this example, we refer to this 0 method as a factory method because it's like a factory. It creates a new object. Now, this example is pretty basic. Creating a 0 point with these initial values is not a big deal. But there are times that initializing an object can be pretty complex. So every time you want to create an object of a given type, you might have to pass some magical values here, and you might have to repeat this in several places in your program. In that case, instead of passing all these magical values to create an object, you can define a factory method that will return an object with these values. And this way you can move this complexity of creating this object into that factory method. Okay, so Let's delete what we have on line 10 and see how we can define a method at the class level. So back to our point class, we define a method, call it 0, and call its first parameter CLS, which is short for class. Again, this is purely convention. We can call this anything, but by convention, whenever we define a class method, we call its first parameter CLS. And as you can guess, this is a reference to the class itself. So here we're not working with a point object or a point instance. Now, to make this method a class method, we need to decorate it with something like this: @class method. This is what we call a decorator, and it's a way to extend the behavior of a method or a function. We'll look at decorators and how they work internally later in this section. So, this is all you have to do to create a class method in Python. Now, in this class method, we have a reference to our class. So with that, we can create a point object with initial values. So we call CLS and give it these initial values. This is exactly like calling point of 0 and 0. The difference is that if we use CLS, at runtime, when we call the 0 method, Python interpreter will automatically pass a reference to the point class to this 0 method. Okay? So we create a point object and then return it. Save the changes. Now, when we run the program, we get a point with these initial values. Throughout this course, I've mentioned magic methods a few times. These are the methods that have 2 underscores at the beginning and end of their name, and they're called automatically by Python interpreter depending on how we use our objects and classes. For example, here we have this init magic method. We don't directly call it. It's called automatically by Python interpreter when we create a new point object. Now, we have quite a few magic methods in Python. Over the next few lectures, you're going to learn about the key ones. But if you want to see the complete list, simply search for Python 3 magic methods. Look at this first page here, a guide to Python's magic methods. I really like this documentation. It's actually better than Python's documentation itself. On this page, we can see various magic methods in different categories with examples. For example, look at the category of representing your classes. These are the magic methods that we have in this category. The first one, stir, is a really useful one, and this is called when we try to convert an object to a string. Let me show you how it works. So back to our code, we have this point object. If we print this on the terminal, see what we get? We get the name of our module, followed by the class name, and the address of this point object in memory. This is the default implementation of the stir magic method in our point object. So, if we type point dot, you can see all magic methods that are available in our point object. We didn't explicitly create these methods. Our point object inherited them from another object. This is what we call inheritance, and you're going to learn about that soon. Now, in this list, you can see we have this stir method. So by default, this returns the name of the class of this object followed by its memory address. Now let's re-implement this method to get a better result. So delete. Back to our class. Let's define this stir method. So 2 underscores, stir, 2 underscore. Now, just like before, the first parameter should be self. Now here, we should simply return a string representation of this point object. So I'm going to return a formatted string. In this string, I'm going to add parentheses. First, we add self.x, then comma self.y. Save the changes. Now, when we print this point object, this is what we get. This is very useful. We get the same result if we also try to convert a point object to a string using the stir function. So, look, we get the same result. So, init and stir are examples of 2 useful magic methods in Python. Over the next few lectures, you're going to learn about other useful magic methods. there are times that we need to compare two objects. For example, here we have this point object. If I define another point object with the exact same values, then compare them and print the result, what do you think we're going to get? Let's take a look. We get false. What's going on here? The reason we get false is that by default, this equality operator compares the references or addresses of these two objects in memory. In this case, these two variables are referencing two different objects in memory, and that's why they're not equal. To solve this problem, we need a magic method. That magic method is called when we compare two objects. So back to this page, here we have comparison magic methods. Let's take a look. So these are all the magic methods we have for comparing two objects. For example, we have EQ for testing equality. We also have NE, which is short for not equal. We have LT, which is short for less than, greater than, and so on. So back to our point class, we need to define EQ magic method. On that page, we can see that this method requires two parameters, self and other. Now, in this method, we need to return true if these two objects are equal, otherwise false. So we can write an expression like this. Self.x equals other.x and self.y equals other.y. So if this expression is evaluated to true, these two objects are considered equal. Now, let's save the changes, run our program one more time, and we get true. Beautiful. Now, what if you want to compare these two point objects like this? If point is greater than other, we run the program, we get a type error because the greater than operator is not supported between instances of the point class. So, to solve this problem, we need to define another magic method. So define GT, which is short for greater than. Once again, we add two parameters, self and other, and write some code like this. Return self.x is greater than other.x, and self.y is greater than other.y. Save the changes. Now, let's modify this value. So I'm going to change the x and y of the first point to 10 and 20. So the first point is greater than the second point. Let's run the program. We get true. Beautiful. What if we change this to less than? Run the program. We get false. So as you see, you don't have to explicitly implement each of these operators. When you implement the greater than magic method, Python would automatically figure out what to do if you use the less than operator. We also have magic methods for performing arithmetic operations between two objects. For example, what if you want to add these 2 points together? When you run this program, obviously we're going to get an error. So back in the list of magic methods, here we have numeric magic methods. In this category, if you scroll down, you can see normal arithmetic operators. So we have add, subtract, multiply, and so on. So in order to add 2 points together, we need to implement the add method. So define add with 2 parameters, self and other. We simply return a new point object with these values, self.x plus other.x. That's our first argument, and then self.y plus other.y. Pretty simple, right? So let's save the changes, run the program. We get this new point object at this address. So we don't see the actual x and y values of this point object because in this example, I removed the stir magic method. However, if we store the result of this arithmetic operation in another object, like combine, and then print combine.x, you can see we get 11, which proves that we successfully added 2 points together. Earlier in the course, you learned about the common data structures in Python. You learned about lists, sets, dictionaries, and so on. These data structures, or container types, are pretty useful and sufficient for most cases. But there are times that you want to create your own custom container types. For example, here we have this class tag cloud. We're going to implement this from scratch together. With this class, we can keep track of the number of various tags on a blog. For example, how many articles do we have that are tagged with Python or JavaScript and so on? So, because this class represents a container, it supports various operations around containers. Here are a few examples. Let me create an object. Okay. Now, because this is a container, we can get the number of items in this container. We can also get an item by its key. For example, we can get the number of articles tagged with Python. We can also set that. And finally, we can iterate over this container. So for tag in cloud, we can print each tag and its count. These are the operations that are supported by this custom container type. So let me show you how to implement a class like this. We create a class, call it tag cloud. Now, internally, we're going to use one or more of the built-in data structures like lists, dictionaries, and so on. In this case, I'm going to use a dictionary because it allows us to quickly get the number of given tag. So first we define a constructor, self, and in this constructor, we initialize tags attribute to an empty dictionary. Now we can optionally add a method like add that takes a tag. Now here we should check to see if we have this tag in our dictionary. If we don't have it, we're going to set its value to 1. Otherwise, we're going to increment it by 1. Here's one way to implement this logic. So self.tags, we use the get method to get an item by this key and supply a default value if we don't have that. Now we get the count, increment it by 1, and finally, we set the value for this key. So self.tags of tag, we set it to this new value. Okay, let's test our program up to this point. So I'm going to create a cloud object and then call the add method a few times. Let's add Python 3 times and then print cloud.tags. Save the changes, run the program. So in our dictionary, we have one key value pair, Python set to 3. Beautiful. Now you might be wondering why I created a custom class instead of using a plain old dictionary. The reason for this is because I want to make this a little bit smarter than a typical dictionary. What if we add a Python tag with the capital P? Technically, this is the same tag as the lowercase python. So when we run this program, we should see one Python tag repeated 3 times. Let's run the program. That's not what we get. We get 2 separate items. This is how a typical dictionary behaves. So in this class, I'm going to take care of case sensitivity. Whatever tag we receive here, we're going to convert it to lowercase when setting it as well as when reading it. Now save the changes, run the program one more time. The problem is gone. Beautiful. So with this class, we're encapsulating the complexity around the case sensitivity of tags. When using this class, we no longer have to worry about lowercase or uppercase characters. So our code looks cleaner and simpler. All that complexity is encapsulated in the tag cloud class. It's not visible to the rest of our program. Okay? Now let's take this to the next level. I want to be able to read the count of a tag like this using square brackets. To do this, we need to implement a magic method called getItem. So define getItem. It should take self as well as a key. In this case, tag. In this method, we're going to return self.tags.get this tag. And if we don't have it, we want to return 0 by default. And once again, we should convert this to lowercase. As we can see, with this implementation, we can easily get the number of a given tag. We can't do this with a typical dictionary. If we don't have the Python tag, our dictionary would throw an error. Now let's take this to the next level. With the current implementation, we can only read the number of a given tag. We cannot set it like this. To do that, we need to implement another magic method called setItem. It's pretty straightforward. So define set item. It takes three parameters: self, key, and value. In this case, our key is tag, and our value is just count. So here we set self.tags of tag.lower to this new count. So with this implementation, we can set the number of a given tag. Now, in order to be able to get the number of items in this tag cloud, we should implement the len magic method. Again, very, very easy. So define len, takes only the self parameter, and here we return len of self the tags. And finally, to make this iterable, so we can iterate over it using a for loop, we need to implement another magic method. That is iter. So define iter. It takes self. Now all we have to do is to use one of the built-in functions to get an iterator object. An iterator object is an object that walks a container and gets one item at a time. So we call iter, which is one of the built-in functions. What do we want to iterate over? In this case, self.tags. So this function returns an iterator object, which gives us one item at a time in a for loop. So we simply return it. This class that we built in the last lecture has a tiny problem. Let me show you. So here we have a cloud object. I'm going to call cloud.add, pass Python, repeat this a couple times, and then change this to an uppercase P. Now, if we print cloud of Python all in uppercase, we get 3. So our program is working. However, if I access the underlying dictionary in this class, our program is going to crash. Let's take a look. So we got an exception of type key error because we don't have this key in our dictionary. Everything is stored as lowercase. So the problem with this class is that it gives us access to the underlying dictionary that is used to keep track of the count of tags. To fix this problem, we need to hide this attribute from the outside, so we cannot access it. How do we do this? Very easy. So back to our class. Put the cursor on this attribute and press F2. This is used for renaming objects in VS Code. Now, to make this private or inaccessible from the outside, you need to prefix it with 2 underlines. Now, when you press enter, you're going to see an error on the bottom right corner of the screen. It's going to tell you that the refactoring library rope is not installed. Go ahead and install that and then try this again. Now you can see all occurrences of self.tags is renamed to self._tags. Now, back to where we use a tag cloud object. If we use the dot operator, so cloud dot, we no longer have tags here. We also don't have _tags. So if we print this, we get an exception of type attribute error. Tag cloud object doesn't have this attribute. So this is how we can make certain attributes or certain methods in the class private. If we prefix them with double underscores, they're considered private. Having said that, technically, these members are still accessible from the outside. It's just a little bit harder to access them. So the point of this practice is not security. It's more of a warning or alert to someone who is using this class. It's telling the consumer of this class, hey, don't touch this. This is private. But let me show you how you can still access this. I'm going to delete all this code. Every class or every object has this property called __dict. This is a dictionary that holds all the attributes in this class. Let's take a look. Print. So in this class, we have this attribute called underline tag cloud, double underlines tags. So when Python interpreter runs this code, it automatically renames this attribute and prefixes it with the name of its class. So technically, we can still access it. Let me show you. I'm going to copy this name and then print cloud dot this attribute. Let's take a look. We get an empty dictionary. So In Python, unlike languages like C# or Java, we don't really have the concept of private members. These private members are still accessible from the outside. Using double underscores is more of a convention to prevent accidental access of these private members. There are times that you want to have control over an attribute in a class. For example, here we have this product class. In the constructor, we set the price attribute. With this implementation, we can create a product object and give it a negative price. And Python interpreter will execute this without any problems. This is not good. So how can we prevent this? How can we ensure that our products don't have a negative price? Here's one simple solution. We can make this field private and then define two methods for getting and setting the value of this attribute. So we define a method called get_price. Here we simply return self.price. And similarly, we define set_price that takes a value. Now here, first we check if value is less than 0, we can raise an exception of type value error, saying price cannot be negative. Otherwise, we set self.price to this new value. Now, in another implementation, instead of raising this exception, we could just ignore setting the value if it's negative. Now, with these two methods in place, we go back to our constructor. Instead of directly setting the price attribute, we call self.setPrice and give it this initial value. When we run this program, our data validation logic is going to kick in and it will throw an exception. Take a look. So we got a value error because price cannot be negative. So this was a simple solution, but it's kind of ugly. It's what we consider unPythonic. Pythonic is one of those expressions that you hear a lot in the Python community. When we say this code or this implementation is not Pythonic, that means it's not using Python's best practices. It's not using the Python language features to the fullest potential. This implementation is the kind of code that a Java programmer learning Python writes. But in Python, we have a better way to achieve the same result. That's when we use a property. A property is an object that sits in front of an attribute and allows us to get or set the value of that attribute. Let me show you how to define a property here. So, in our product class, after we define these two methods, we define a class attribute with the ideal name. In that case, we want to call that price. Here we call the built-in property function. This function takes 4 parameters, and all these parameters are optional. The first parameter is a function for getting the value of an attribute. The second parameter is a function for setting the value of that attribute. The third parameter is a function for deleting that attribute. And the last parameter is for documentation. In this case, we need to supply 2 arguments. The first one is going to be getPrice, and the second is going to be setPrice. Note that I'm not calling these methods. I'm simply passing a reference to them. So when we call the built-in property function, with these arguments, this function will return a property object. That property object will use this function for reading the value of the price attribute. Now, by adding this line, we can come back to our product. Let's set the initial price to 10. Here, when we use the dot operator, you can see we have this price property, and we can use it like a regular field. So we can simply print it here, and we see 10 on the terminal. And also, we can set it, but if we set it to a negative value, this will throw an exception. Let's run our program. There you go, value error. So a property looks like a regular attribute from the outside, but internally it has 2 methods that we call a getter and a setter. Now, while this price property solved our problem, the 2 methods that we wrote are still accessible. So if we type product dot, you can see we have getPrice and setPrice methods. These methods are polluting the interface of our object. As a metaphor, think of a remote control with 50 buttons. Nobody likes that kind of remote control. It's so confusing. It's much better to have a remote control with few buttons that can do a lot. We want our objects or our classes to be the same. We want them to have minimal number of functions or methods exposed to the outside. So, to hide these, one solution is to come back and make them private. But again, this adds extra noise in our code. There is a better, shorter, and cleaner way to achieve the same result. We can use a decorator. Remember decorators? Earlier, we used a decorator called class method to convert an instance method to a class method. We have another decorator for creating a property. So instead of explicitly calling the property function to create a property object, we can apply the property decorator to this method. Then we rename this method to the ideal name. In this case, we want to call it price. When Python interpreter sees this code, it will automatically create a property object called price. Now, similarly, we need to apply another decorator to this method. The name of that decorator starts with the name of our property, in this case, price, and then dot setter. Also, similarly, we need to rename this method to price. So our implementation is cleaner, it's less noisy. We don't have that get underline and set underline. This is much better. Now, how this works internally is a little bit complicated, and we're going to look at that later in the future. For now, all you need to take away is that with these two decorators, you can easily create a property. Now, there is one more place that we need to modify here, and that is our constructor, because we no longer have set price. But the good thing is that we can use our price property like a regular attribute. So we set self.price to price. With this new implementation, if we try to create a product with a negative price, our code will throw an exception. Let's take a look. There you go, value error. Now, one last thing before I finish this lecture. When defining properties, you don't always have to define a getter and a setter. In this case, if we comment out these few lines, we'll have a read-only property. So we can only read the value of this price. Once we set it, we cannot change it. So we can initially set it to, let's say 10. But if we try to update it later, we'll get an exception. So if we set product.price to 2 and run this program, we get an attribute error because we can't set that attribute. So this is all about properties. As you build various classes, you may notice that some of these classes might have one or more features or functions in common. Here's an example. I'm going to create a class called mammal. All mammals should be able to eat, right? So let's define a function called eat. And in this function, we simply print eat. Now, all mammals, as far as I know, should be able to walk. So let's define another method, walk. And in this method, we print walk. Now, I'm going to select all this code and hold down Shift, Alt, and down arrow to duplicate this class. Now, let's rename this second class fish. As we know, all fish should be able to eat, but fish don't walk, they swim. So let's change the second method to swim, as well as this message that we print. Now, what is going on here? As you can see, we have repeated or duplicated the eat method in both these classes. Now, in this implementation, our eat method is only a single line of code, but in a real-world program, you might have a method that is 5 or 10 lines of code, and you might have repeated that in multiple classes. This is bad, because if there is a bug in one of these methods, you have to fix it in multiple places. Or similarly, if you need to change the behavior of this method, then again, you have to do it in multiple places. In programming, we have this concept called DRY, which stands for don't repeat yourself. So we don't want to repeat ourselves. To solve this problem, we have two solutions. We can use inheritance or composition. In this lecture, we're going to look at inheritance, and I'm going to talk about composition later in this section. Inheritance is a mechanism that allows us to define the common behavior or common functions in one class, and then inherit them in other classes. Here's how it works. So I'm going to define a separate class called animal, and then move the eat method in this class, like this. Now you can see our mammal class is simpler. So to have it inherit the eat method from the animal class, we simply add parentheses here and then specify the animal class. This is inheritance in action. We say the mammal class is an animal, so it inherits all the features or all the methods of the animal class. In this situation, we refer to the animal class as the parent or base class and mammal as the child or subclass. So let's go ahead and apply the same change on the fish class. We get rid of the eat method and add animal as the base class. Now, when we create a mammal object like M, you can see this mammal has both the eat and walk methods. So let's call eat, run the program. We see this message on the terminal. So this verifies that our mammal class inherits from the animal class. Now, this inheritance is not limited to methods. We can also inherit the attributes of a base class. For example, back to our animal class, I'm going to define a constructor. And in this constructor, let's set age to 1. Now, when we create a mammal object, our mammal object will automatically have the age attribute initialized to 1. Let me show you. So back here, let's print m.age. There you go. Run the program. Here's the result. So this is the basic of inheritance. Now, in real programs, we don't build animals or mammals or fish, unless we're building a game. But I use this as an example because it's easier to understand the relationship between a mammal and an animal. Later in this section, I'm going to give you a real-world example of inheritance in our programs. So in the last lecture, we defined this mammal object. Now let me show you a couple of useful built-in functions. We have this function isInstance, and it tells us if an object is an instance of a given class. So if we pass M and mammal here, obviously this M object is an instance of mammal. So when we print the result, we should see true. What if we pass animal here? Let's run the program. We still get true. Because mammal inherits from animal, so an instance of the mammal class is also an animal. Now let me show you something interesting. This animal class that we defined here inherits from another class called object, even though we didn't add that here. So we have a class called object, and that is the base class for all classes in Python. So every class that we have directly or indirectly derives from the object class. Let me show you. So let's delete this and go back to line 18. Let's see if M is an instance of object. Run the program, we get true. So mammal inherits from animal, which inherits from object. We also have this built-in function for creating an empty object. Now, if we inspect this object, you can see all these magic methods. These are the magic methods that every class in Python has. So if we type m dot, you can see our mammal class or our mammal object also has these methods because it inherited them from the base object class. We have another built-in function that you might find useful in certain situations, and that is subclass. And with this, we can see if a class derives from another class. So let's see if mammal is a subclass of animal. Print the result. Obviously, we get true. Now, if we change animal to object, we still get true because mammal indirectly derives or inherits from the object class. In this example, our animal class has this constructor where we initialize the age attribute to 1. What if we want to add a constructor to the mammal class and initialize its weight? Let's do that and see what happens. So to save time, I'm going to copy these two lines, and then paste them in the mammal class. Now, instead of the age attribute, I'm going to set the weight attribute to 2. With this, let's print m.age as well as m.weight. Run the program. We got an attribute error because mammal object has no attribute age. The reason this happened was because this constructor in the animal class was not executed. In other words, this constructor that we defined in the mammal class replaced the constructor in the base class. This is what we call method overriding. So we are overriding or replacing a method in the base class. Now, what if we still want to execute this constructor and initialize the age of an animal? That's very easy. Here in the constructor of the mammal class, we can use the built-in super function to get access to the super or base class, which is in this case animal. So we have an access to the animal class. Now we can call any of the methods in this class. So let's go ahead and call the init method. Now to see the execution flow, I'm going to add a print statement here and print mammal constructor. Similarly, here in the constructor of the animal, I'm going to print animal constructor. Let's save the changes and run the program to see what happens. As you can see, first, the constructor of the animal was called. So here we set the age to 1. Then the constructor of the mammal was called, where we set the weight to 2. And finally, we print 1 and 2, which are the results of these two statements. Now, we can also change the order of these method calls. So we can call the constructor of the animal after we initialize a mammal object. So here in the mammal class, instead of calling super.init first, we're going to do it after we do all the basic work in the mammal constructor. Let's save the changes and run the program. As you can see, the constructor of mammal was called first, and then we have the constructor of the animal. So to recap, method overriding means replacing or extending a method defined in the base class. In this implementation, we're extending the init method that we have defined in the animal class, because here we do some work in the constructor of the mammal, and then we call the constructor of the animal. If we didn't have this line here, this implementation would completely replace the init method in the animal class. So you have seen that inheritance is a good thing. It prevents code duplication and allows us to reuse code. For example, here we have this bird class that inherits from the animal, so it inherits all the features of this animal class. In this case, we are reusing the eat method here. That's pretty good. However, too much of a good thing is a bad thing. And that's very true about inheritance. Because too much inheritance between classes can increase complexity and introduce various kinds of issues. Let me show you an example. Here I'm going to define a class called chicken. Well, a chicken is a bird, so we can inherit it from the bird class. And here I'm going to use the pass statement to define an empty class. So as I've told you before, pass is a statement that doesn't do anything. We just use it to make Python interpreter happy because we cannot have a class without anything in it. We need to have at least one statement. So here we have the pass class. But there is a problem in this code. What is the problem? Well, the chicken class inherits all the features of the bird class, but a chicken cannot fly. So with this implementation, I can create a chicken object and call the fly method on it. So this is an example of inheritance abuse. Another example of inheritance abuse is around the concept of employees. And I've seen that a lot in my career. So some people say, well, an employee is a person, and a person is a living creature, which is a thing, blah, blah, blah. This is what we call multi-level inheritance, which can significantly increase the complexity of your software. To tell you a little story, in one of my previous jobs, we had this consultant and he was charging like $150 an hour or more. And he came up with a huge inheritance hierarchy like this. In fact, 3 times bigger than this. There were so many levels, and he essentially tried to model the entire universe. This is really, really bad. Just because an employee is a person and a person is a living creature in the real world doesn't mean you should have classes like this in your software. The methods you add in your classes are there to solve a business problem. That is the focus of your software. So just because an animal can eat in the real world doesn't mean your animal class should also have the eat method. You got the point, right? So this is multi-level inheritance and you should avoid it at all times. If you want to use inheritance, limit it to 1 or 2 levels. Going beyond that, trust me, you're going to shoot yourself in the foot. In Python, a class can have multiple base classes. So here we have this manager class that has 2 base classes, employee and person. This is what we call multiple inheritance. And similar to multi-level inheritance, it's a source of issues. If you don't use it properly, you're going to introduce all sorts of bugs in your programs. Let's take a look at an example. So in this employee class, we have a greet method. And in this method, we simply print employee greet. Our person class also has the exact same method, but here we print a different message. Now, our manager class currently has no implementation. It simply inherits all the features of the person and employee classes. Now, let's see what happens when we create a manager object and call the greet method. Which greet method do you think is going to get called? Let's take a look. So, I'm going to define a manager and call manager.greet. Let's run the program. We get employee greet because we added the employee class first. So when Python interpreter tries to execute this line, first it looks at the manager class to see if it has a method called greet. If it doesn't, it will look at its first base class. Does the employee have a greet method? Yes. So the lookup terminates here. If the employee class doesn't have the greet method, then it will look at the person class. So why is this an issue? Because if tomorrow another programmer joins our team, and for whatever reason, they decide to change the order of these base classes, our program will have a different behavior. So if they move this person class over here and run the program, now we get a different output. So similar to multi-level inheritance, multiple inheritance can create all sorts of issues in your programs. You will end up with classes that inherit features that they shouldn't, like a chicken that flies. So if multiple inheritance is a bad thing, why does Python support it? Well, multiple inheritance is not always a bad thing. It's bad if you don't use it properly. If these classes that we have here, they're small classes and they have absolutely nothing in common, and you want to inherit their features in a separate class, that's perfectly fine to use multiple inheritance. Things start to get complicated when these classes have things in common, like the greet method here. So let me show you a good example of multiple inheritance. Here we could have a class called flyer. It's any object that knows how to fly. So let's add fly here. So it's a very simple abstract concept. Similarly, we could have another class called swimmer. It's an object that knows how to swim. Now, as you see, these two classes are very small and abstract. They have nothing in common. Now we can combine the features of these two classes so we can create a flying fish that knows how to fly and how to swim. So it's a flyer and also a swimmer. This is a good example of multiple inheritance. Now let's look at a good example of inheritance. Let's imagine we want to model the concept of a stream of data. We can read a stream of data from a file, from a network, or from the memory. All these streams have a few things in common. We can open them, we can close them, we can read data from them, but how we read data from a stream is dependent upon the type of the stream, because reading data from a file is different from reading it from a network. So let's start by defining a base class called stream. In this class, I'm going to define methods like open and close. So define open. Now here, let's say we need a flag to know if the stream is open or not. So we can define a constructor. And in this constructor, we can set the opened flag initially to false. When we call the open method, we can set this to true, like this. Now, what if we try to open a stream that is already open? That is an invalid operation. So perhaps we want to raise an exception. So we can check if self.opened, we want to raise an exception. What kind of exception? Well, we don't want to do a value error because here we're not dealing with a value. In this example, we can create a custom exception called invalid operation error. We don't have this in Python. In this case, we can create a custom exception called invalid operation error because we don't have a built-in exception in Python that represents this concept. So on the top, let's create another class, invalid operation error. So by convention, all custom exceptions should end with error. Now we want to derive this from the base exception class in Python. So every time you want to create a custom exception, you should derive your class from the exception class. Now here we don't need any code, so we simply add a pass statement. Back to our open method. If the stream is already open, we want to raise an invalid operation error. And here we can give a friendly message like stream is already open. So this is our open method. Now let's define the close method. That's going to be very similar. So to save time, I'm going to copy these few lines and rename this method to close. Now here we want to check if the stream is already closed, you want to raise an invalid operation error. So if not self.opened, we should raise this exception and change the error message to stream is already closed. And finally, here we set open to false. So these are the common features that we need in every stream. Now let's go ahead and implement a file stream. Oops, actually I have a typo here. Sorry about that. So we define another class, file stream, which inherits from our stream class. Now, as I told you before, how we read data from a file is different from how we read it from a network. So I'm going to define a method called read. And for simplicity, let's just print reading data from a file. Save the changes. Now, let's duplicate these few lines and create a network stream class. Network stream. And we should also change the message to reading data from a network. This is a good example of inheritance because first of all, we don't have multi-level inheritance. We only have 1 or 2 levels depending on how you want to calculate it. So we have the stream class on top of our hierarchy, and below that we have 2 subclasses, file and network stream. Now it's okay if we add another level of inheritance here, but we shouldn't go beyond that. Also, as you can see, we don't have multiple inheritance, so our subclasses don't have multiple parents. We're going to continue with the example from the last lecture. There are a couple of issues with this implementation. The first issue is that we can create a stream object and call the open method. Why is this an issue? Because this stream class is an abstract concept. What does it mean to open a stream? Are we working with a file stream here, a network stream? What kind of stream? So we shouldn't be able to directly create an instance of the stream class. We should always subclass it and then create an instance of the subclass. That is the first issue. So we only created this stream class as a base class to provide some code that we're going to reuse across different kinds of streams. This is the first issue. Now the second issue. If you look at the implementation of file stream and network stream classes, you can see both these classes have a read method. If tomorrow we decide to create a different kind of stream, we should remember to implement this read method and call it exactly read. If we call it readline or read str or read whatever, it's not going to be consistent with the other kinds of streams that we have here. In other words, currently there is no way to enforce a common interface across different kinds of streams. This is more of a convention we have used here. It would be nice to have a common contract or a common interface across these different types of streams. So how can we solve these problems? That's when we use an abstract base class. An abstract base class is like a half-baked cookie. It's not ready to be eaten. It's half-baked. It's half-cooked. Its purpose is to provide some common code to its derivatives. So here we want to make this stream class an abstract base class. To do that, we go on the top and from ABC module, which stands for abstract base class, we import the ABC class and abstract method function, which we're going to use as a decorator. So make sure to type this exactly like what you see here. So the name of the module is all lowercase and the name of the class is all uppercase. Now, to make this stream class abstract, we should derive it from the ABC class, abstract base class, okay? That is the first step. The second step is to define the common interface for all streams. We want all streams to have a read method and potentially a write method in the future. So here we define a read method. This method has no implementation. So we simply pass here. Now we need to decorate this method with abstract method decorator. With these two simple steps, we fix both the problems I talked about in this lecture. So now, if I save the changes and try to run the program, you can see we immediately have this red underline with abstract methods instantiated. Basically, when a class has an abstract method, it's considered an abstract class, and we cannot instantiate them, which means we cannot create an instance of them. So when we run this program, we get this type error, okay? Now let's look at the second problem. So let's say tomorrow we're going to create a new kind of stream. We call it memory stream, and we derive it from the stream class. For now, let's just pass and create a memory stream object. Once again, you can see we have a red underline, abstract class with abstract methods instantiated. What's going on here? In our stream class, we defined an abstract method called read. Let's take a look. Here's our abstract method. If a class derives from the stream class, it has to implement this method. Otherwise, that class will also be considered abstract. So in this example, our new class, memory stream, is also abstract. If we want to make this a concrete class so we can instantiate it, we'll have to implement the read method. So define read, and here we print reading data from a memory stream. Now, this memory stream is a concrete class. We can instantiate it here, and it also follows the contract or the interface of the stream class. So all our streams now have a read method. So in the last lecture, you learned about abstract base classes. As another example, here I have defined an abstract base class called UI control. This class has an abstract method called draw, and as you can see, this method has no implementation. So this class only defines the contract or the interface that all its derivatives should follow, okay? Now, here we have two classes that derive from UI control. One is textbox and the other is dropdown list. Both these classes implement the draw method. Here we simply print textbox, and in the dropdown list class, we print dropdown list. So nothing new so far. Now, here we also have a function called draw that takes a UI control object and calls the draw method on it. So with this, I can create a dropdown list object, dropdown list, and pass it to this draw function like this. This should be perfectly fine because the dropdown list is an instance of the UI control class. To verify this, let's call isInstance function and pass this DDL object as well as the UI control class. And then print the result on the terminal. For now, I'm going to comment out this line. So save the changes and run the program. We get true. So a dropdown list object is an instance of UI control. And that means wherever we expect a UI control object, we can pass any of its derivatives, like a text box or a drop-down list, right? So let's delete this line and call the draw function with this DDL object. What do we see? We see a drop-down list. Now, what if we pass a text box to this function? Let's take a look. So I'm going to create a text box like this, and then pass it to this draw function. Run the program. This time we get text box. Now you might ask, what is the point of this? Well, let's take this to the next level and make it more interesting. I want to change this draw function. So instead of getting a control object, I wanted to get a list or a tuple of controls. So let's rename this to controls. And here we'll use a for loop to iterate over this controls object. So for control in controls, we call the draw method on each control object. Now, we're going to pass a list of two objects, a drop-down list, and a text box. Let's run the program and see what happens. As you probably expect, we get two messages, drop-down list and text box. So using this approach, we can render the user interface of an application. Imagine we have a form with a bunch of text boxes, drop-down lists, radio buttons, and so on. We could have a list of all these objects and pass that list to a function like draw, and that function would take care of rendering the entire form. What is interesting here is that our draw function doesn't know what kind of control it's working with. This is determined at runtime. It simply iterates over the list of controls and calls the draw method of each control object. This is what we call polymorphism. Poly means many, morph means form. So polymorphism means many forms. In this example, our draw method is taking many different forms, and this is determined at runtime. We could be calling the draw method on a text box, or a drop-down list, or a radio button, and so on. So this is the classic example of polymorphism. What you saw in the last lecture was the classic example of polymorphism. So to achieve polymorphic behavior, we start by defining a base class. And in this class, we define the common behavior or the common methods that we need in its derivatives or children. With this, we achieve polymorphic behavior in our draw function on line 22. So depending on the type of control object that we're working with at runtime, this draw method takes a different form. It might be the draw method in a text box, or a drop-down list, or a radio button, and so on. So this is how polymorphism works in pretty much all languages that support classes. But because Python is a dynamically typed language, we don't necessarily need this UI control as the base class here. In other words, if we get rid of this class, let's just delete it for now. We should also delete it from these two places. With this change, we can still achieve polymorphic behavior. Why? Here is the reason. Look at this controls parameter. Nowhere here we have specified the type of this parameter, right? This is purely a label, a name. We can pass any kind of objects to this draw function. As long as that object is iterable, Python will be happy. Because here on line 15, we are looping over that object. So that object has to be iterable. So technically, we can pass a string, a list, a tuple, a dictionary, anything that is iterable here. By the same token, that iterable object, its individual parts, should have a draw method. So Python doesn't care if these objects derive from the UI control class. As long as these objects have a draw method, Python will be happy. This is what we call duck typing. So if it walks like a duck and quacks like a duck, it is a duck. That is how Python works. Because Python is a dynamically typed language and it doesn't check the type of objects. It only looks for the existence of certain methods in our objects. In other words, in this case, on line 16, it only looks for the existence of the draw method. So if this object has a draw method, Python assumes it's a UI control. It's exactly like saying, if it walks like a duck and quacks like a duck, it is a duck. So to achieve polymorphic behavior, we don't necessarily need a base class like UI control because Python supports duck typing. Having said that, having that UI control as an abstract base class is a good practice because it enforces a common interface or a common contract across all its derivatives. With this, we'll make sure that every kind of UI control will have a draw method. In Python, we can also use inheritance with the built-in types. For example, we can create a class called text and have it inherit from the built-in string class. With this, our text class will inherit all the features of Python strings, but we can also add additional features to it. For example, we can add the ability to summarize it or duplicate it and so on. So let's define a method called duplicate that takes self. And in this method, we'll simply return self plus self. So let me explain what's going on here. As I told you before, self represents the current object, which is in this case an instance of a string class. So here we're concatenating a string with itself. Now we can easily use our text class. So let's add Python, store the result in this variable. Look, our text object has all the methods of Python strings. So we can convert it to lowercase and print it. And here's the result. But we can also duplicate it. So when we duplicate it, we get a new string, which is Python. Pretty useful, right? As another example, we can also extend Python lists. So let's define a new class, call it trackable list that inherits from the built-in list class. Now here I want to override the append method. So every time we want to append an object to this list, we want to print a message on the terminal, perhaps for logging. So let's print append called. Now we want to call the append method of the superclass, the base class. So we call super.append and pass this object. So here, technically, we are extending the append method of the list class. We are not replacing it, okay? Now, we can create a list object using trackable list, call the append method, and when we run this program, you can see this message on the terminal. So as you see, extending built-in types in Python is really easy. So you have learned that we use classes to bundle data and functionality into one unit. Now, as you work on larger programs, you may come across classes that don't have any behavior. They don't have any methods. They only have data. Here's an example. We have this point class that has two attributes, x and y. It doesn't have any methods. Now with this, we can create 2 point objects. So P1, we set it to point of 1 and 2, and P2, the same. Now, when we compare these two objects and print the result, we get false because these two objects are stored in different locations in memory. So by default, Python compares objects based on where they're stored in memory. If two variables are referencing the same object in memory, they're considered equal. In this example, our point objects are in 2 different locations, even though they have the same attributes. So to prove this to you, I'm going to call this built-in ID function. This returns the address of the memory location where an object is stored. So let's look at the address of P1 and also P2. As you can see, these objects are in 2 different locations in memory. So to solve the issue with comparing point objects, we need to come back here and implement a magic method, EQ. This method takes self and other, and here we should compare self.x with other.x and self.y with other.y. Now, when we compare these two objects, P1 and P2, we get true. So the problem is solved. However, writing all this code for data classes is a little bit tedious. If you're dealing with classes that have no behavior, no methods, they only have data, you can use a named tuple instead. Let me show you how that works. So let's delete this. On the top, from the collections module, we should import the named tuple function. We call this function. As a first argument, we specify the name for this new type we want to create. So we're going to call that point. So note that I'm passing a string here. Now, as a second argument, we pass an array of field names or attribute names. We want our point objects to have two attributes, x and y. So this returns a name tuple that we can store here. Note that I'm using Pascal naming convention because point here represents a type, like a class. So we can call it to create a new point object. However, instead of passing these arbitrary values here, we should pass keyword arguments. So we set x to 1 and y to 2. The first improvement here is that our code is more clear and less ambiguous. We don't have to wonder, what are these values? Now, point is a simple concept. It's easy to guess that 1 and 2 represent x and y here. But sometimes when creating objects, you might have to pass some magical values, and someone else reading that code, they don't know what these values represent. So, these keyword arguments make our code more clear. The second benefit is that we don't have to explicitly implement a magic method to compare two objects. So if we have 2 point objects with the exact same attributes, we can easily compare them and we get the result that we expect. So if you're working with classes that have only data and no methods, you might want to use a name tuple instead. You will write less code. And these name tuples are better than regular tuples because here we'll have attributes in this point object just like the attributes we have in our classes. So if we print p1.x, we see 1. Just be aware that these name tuples are immutable, which means once we create them, we cannot modify them, we cannot mutate them. So if I set p1.x to a new value and run the program, we get an attribute error because we can't set an attribute of a name tuple after we initialize it. So if you really need to modify one of these values, you need to create a new point object. So we set p1 to a new point with x set to 10 and y set to 2. So this is all about name tuples.